Vibration analysis. Data collection. Accelerometer. 3 different accelerometers are required in most plants. Figure 4 contains a photo of an piezoelectric accelerometer. Number 1 is low-frequency accelerometer. This is required to measure the low frequencies that cannot be measured with a displacement transducer, for example, low-frequency vibrations in buildings, the earth, and some radar antennas. The frequency response of these accelerometers is from DC to about 500 Hz. Since low frequencies generate low G amplitudes, the sensitivity is often 500 mV per G or more. Number 2 is medium frequency accelerometer. A medium-range accelerometer is also required for various measurements. The frequency response is often from about 2 Hz to about 10 kHz. However, the sensitivity may vary 15 or 20% on the high end. The sensitivity of these accelerometers is often 100 mV per G. Number 3 is high-frequency accelerometers. These are also required in most plants. These accelerometers can measure frequencies up to 100 kHz, however the amplitude accuracy may be more than 20%. The transducer sensitivity is often 25 mV per G or lower because high frequencies generate high G levels. The mounting of the high-frequency accelerometer is quite critical. The transducer should be screwed down, the mounting surface should be machined, and a couplant should be used between the transducer and machine surface. Most accelerometers are based on the piezoelectric crystal principle. A piezoelectric crystal responds to a mechanical motion by generating an electric voltage. The voltage amplitude is quite low, in the microvolt area, 1x10⁻⁻⁶. The piezoelectric crystal responds to an electrical voltage with a mechanical vibration. These crystals are used in this manner also for delay lines in some radar applications. In most applications, the frequency response of a crystal is determined by size. The larger the crystal, the lower the frequency. The smaller the crystal, the higher the frequency. Since the output of a crystal is so low, the signal must be amplified in, or very close to, the accelerometer. If this amplification is not accomplished, the signal may get lost in the electronic noise. When the accelerometer is used, it should be hard-mounted, i.e. either glued or screwed down. A large segment of industry is collecting data with handheld accelerometers, or accelerometers with a magnetic base. Such practice should be discouraged because some frequencies can be over or understated by as much as 12 dB, about 4 times the actual. Also, if you use the zoom feature, the resulting frequency window may contain noise rather than discrete frequencies. The reason data collected with a velocity transducer using a magnetic base are acceptable is because the velocity transducer is more forgiving. For example, a slight amount of movement caused by the mounting of the velocity transducer may not be observable with the unaided eye. This is true because first, the sensitivity is high, about 400 mV per inch per second. And the second, because of the roll-off of the frequency response at the low end. Also, looseness is a low-frequency phenomena. By contrast, all motion of the accelerometer is amplified. Thank you.